Yeah, so thank you for the invitation. I wish I could be in UCLA in person, but that cannot happen. I have fond memories from the campus, but we will do it remotely. So today's talk will be on learning with few label data. Uh, and here is how I would like to structure it. So the first half of the talk, or let's say the first 40% of the talk, will be on what is called few-shot image classification. And I'll tell you what it is. Image classification systems, which have access to very little data during training. The next part of the talk is what I call a thermodynamical view of representation learning. And this is kind of a much more abstract, more formal way of looking at transfer learning and more information theoretic ideas behind it. So let's begin. There are really three regimes of image classification. The first one is what one would call high shot regime. Let's say I give you 10 to 1,000 samples per class of cars, cats, dogs, planes. These are classes that are very frequent. On the internet, you can collect a lot of images about these classes and train models. ImageNet is a big data set that some of you might know, but 1,000 classes, 1,000 samples roughly per class. And it is fair to say that this is the regime that we've become really good at handling. Neural networks are good at image classification, and they're good if I give you roughly 100 samples per class. Where they don't work well is what one would call the low shot regime. So let's say I don't have 100 images or 1,000 images of one class anymore. I'm thinking of classifying the three different kinds of strawberries that are grown on a farm in California. And now the farmer doesn't understand why, if I'm so good at image classification, I need more data from him. So he gives me 5 images of these 3 strawberries. So at the end of the day, I have 15 images labeled of 3 kinds of strawberries. And this is the kind of classification problem that I'm interested in solving. It's low shot meaning few images per class, roughly speaking, of the order of 10. The third regime is what one would call extreme low shot regime. In this case, let's say you look at a rare insect, you're trying to understand whether or not you've seen this insect before. This is more of an anomaly detection problem, or some people would also like to formalize this as an open universe classification setting. Roughly speaking, low shot regimes and extreme low shot regimes are areas which we haven't managed to make good progress yet. These are pertinent problems because the world doesn't look like ImageNet. The world is not 1,000 classes, 1,000 images per class. The world is really a million of classes, millions of classes. And some of them are very frequent, like cars and cats. Some of them are very rare, like these 3 strawberries. And what you want to do is build systems that bootstrap their learning from the frequent classes and then kind of dig deeper into the tail of these rare classes. And let us try to formalize the problem. So I have a bunch of classes that are frequent: cars, cats, dogs, and planes. I collect as much data about them as I can. And I call this my training set. The training set in this problem consists of a lot of different tasks. Now, we don't really have a good way of asking ourselves what a task is for the purposes of this talk. I'll think of a task as a category. Cars is one task, cats is another task. That is the training set. The test set, or the new task, let's say classifying strawberries, comes in the following form. So I give you W different classes. W is what is called the ways in this particular literature. These are the different number of new strawberries that I'm interested in classifying. 3 for the case of the farm. For each of this class, I give you S labeled images of that class. S is what is called shots. And really, few shot setting simply implies that the number S is small. It is much smaller as compared to what I have in the training set. If the training set has 1,000 images per category, I may be interested in classifying with only 10 labeled data of the new classes. This is what is called few shot learning or few shot classification. And here is one flavor for how these algorithms look like. Some of you may have heard about this thing called meta-learning. Meta-learning is a general umbrella for solving these kinds of classification problems. And the way to summarize meta-learning is as follows. So if I have a lot of different tasks, let's say the task in my meta training set to learn from, I would like to learn one classifier for each of these base tasks. And I would like to learn what is called a meta classifier, which tries to consolidate information from these base classifiers. And then when I get a new task, a meta classifier's job is really to create a classifier, to instantiate a new classifier that presumably works well on the new task. So think of SVMs, but then think of SVMs working on top of SVMs, that the meta level creates a new SVM itself that works for the new task. This is what is called meta learning. Let's take one example of how meta learning is instantiated in practice today. You can look at this paper called Prototypical Networks. It works in a similar fashion. It collects a meta training set that is a large number of tasks. It trains one single model for classifying all these tasks. And the key is that because this model is not being used to classify categories of the meta training set, we would like it to classify categories that are new. You don't want to train this model for classification. You really want to train this model for clustering. You train it for clustering in such a way that the features of this model are clustered together. The features of images of the same class are close by. Features of images of different classes are far away from each other. And now when I give you a new task, it is easy to use this model. You simply feed the new images through the model. Let's say the new model had 3 different classes. C1, the little green circles are all the features of images that belong to the label data in the class C1. I know by virtue of the labels the mean of their features. And now I have a nice Gaussian mixture model that I can use to predict the labels of unknown data. Let's say the white datum that lies in this particular spot. So it has a particular affinity to belonging to class C2. It has a slightly lower affinity of belonging to class C1. I will call it a datum of class C2. So roughly speaking, meta learning, the way it is instantiated, is some kind of metric learning. There are details of how these models are trained. Those are not terribly important for the purpose of this talk. But the idea is to create these kinds of classification systems that will work with new categories. How well do these algorithms work today? Well, let us look at this plot. So the x-axis is 5 different algorithms. These are roughly ordered in chronologically between when they were discovered. The first one is prototypical networks, the one that we just saw. MAML is a popular gradient-based instantiation of meta-learning that was also discovered around 2017. The other 3 are the newer ones. The y-axis shows what I call one-shot 5-way accuracy on this dataset called mini ImageNet. One shot means one labeled image per new class. 5-way means 5 new classes that I'm forcing the model to classify. And this is a box plot. So the horizontal lines inside the box are the median performance of this algorithm on new tasks. I gave it 1,000 different new tasks of 5 classes each. And then I'm evaluating what is the average accuracy and what is the mean accuracy, standard deviation of the accuracy of the algorithm across all these tasks. So the horizontal line is the median. The box denotes, half box denotes 25 percentile, and the whiskers denote 99 percentile in total. And what you will immediately notice is that as we've moved on from 2017 to, let's say, 2020 today, roughly speaking, you see an increasing trend in the mean accuracy of these algorithms. What people did not quite realize until now is that the error bars on the mean accuracy are so enormous. So is it really fair to say that we are making progress? Well, to an extent, we are making progress in the mean accuracy, but the inherent variance in how we evaluate these algorithms is so large that it is difficult to say that these algorithms are better or worse than each other. They are roughly the same, any statistician would tell you. And this is really a picture that kind of started this work. We would like to understand what is it that makes these algorithms so finicky, so difficult to get to work, and what is it that we can do to improve these things. Let us look at the one key idea behind this work. It's a very simple idea, and it goes as follows. So suppose I give you a data set DS, and I give you a test datum X that I would like to classify. Classifying a test datum really boils down to you pulling out a function f from your hat, saying f is a function of my new datum X and my training set DS, and I would like it to predict the labels of my new datum. So machine learning 101, the function f is what we are trying to find. Now, machine learning takes the perspective of boiling down this function into a bunch of parameters. Instead of searching over all these functions at test time explicitly, I choose to maintain parameters theta star. Theta star are now a function of my training data set. These are the parameters of my model after training the model. And I choose to store these parameters on my hard disk. Why? Because I don't like to search over all the space of all functions f at test time. And I can amortize the cost of inference by forcing myself to spend more time in training and maintaining theta. Theta is really like a sufficient statistic of the dataset ds that you would like to learn. The name of the game in few-shot learning is that because your training data set is too small, I only gave you 5 images of these new strawberries. There is really very little you can learn about the sufficient statistic of this data set. You cannot learn a good parametric classifier that classifies new data even from those strawberries. So we are going to kind of come up with some mashup of standard machine learning and this very explicit search over the function space, and that goes as follows. So the first term in this loss function is simply the cross entropy loss, improving the likelihood of data of your labels given data as standard. The first ns images are the images of your training set. The last image, ns plus 1, is the one that is your test data. So by explicitly optimizing your parameters over both your training set and your test set, you are improving the performance on the test set, even if the test set is consists of very few label data. Of course, you don't want to do this entire business from scratch at test time because it is too expensive. And you choose to keep your parameters theta close to some pre-learned parameters theta star that are a function of dataset of the training dataset ds. So in simple words, this entire formula boils down to you training a model on your training dataset and then fine-tuning this entire model on all your training data and the new unlabeled test data. Notice the arg minimization over the unknown labels. The one that maximizes the probability is the one that I predict to be the correct class of this data. So a very simple explicit search over the space of functions, a simple fine-tuning. This has a name. This goes under the banner of what is called transductive learning, and focus on the image on the left-hand side. If I take a binary classification problem, let's say positives are class 1, negatives are class 2, I could be interested in finding the maximum margin hyperplane that separates these two classes. This would be the dotted line. This is standard SVM, for instance. If at test time, I gave you a little more data, of course, it is test time, so I don't give you the labels of this new data, and these are shown by these empty balls on the figure on the right-hand side. You may be inclined to change your hyperplane, which is horizontal on the left-hand side, to be a little more inclined. You know that there are two, this looks like a more reasonable hyperplane that is likely to do well. Of course, there are caveats. If I did not give you enough empty circles, if I gave you empty circles antagonistically, then you will make mistakes when you try to adapt this hyperplane to the new unlabeled data. So transductive learning is different from inductive learning. Inductive learning is the left-hand side where I don't adapt the hyperplane before making predictions or test data. Transductive learning adapts the hyperplane from the learned from your training data set's hyperplane every single time it would like to do inference. This is expensive, but you get better accuracy. And the idea is that in the few-shot setting, this hyperplane was learned very inaccurately to begin with. So you get a lot of benefit by adapting it to a little more test data. This is transductive learning. So this particular expression is really what one would call transductive fine-tuning. Fine-tuning would have done would have simply fine-tuned on the old data on some labeled data. Transduction also uses unlabeled test data to do the fine-tuning. So here is one idea. We train a very large neural network on the very large meta-training data set that I have created. Larger the better, such is the rule. I'm training very large neural networks. I don't really care about their performance on the meta-training data sets. I'm going to regularize them very, very heavily because I don't want them to overfit at all. I want them to be more malleable when I do transductive fine-tuning. I initialize what one would call a classifier head on top of the network itself. So typically when people do fine tuning these days, you take a network, you chop off the last layer of the network, and then you insert a new layer for classifying the 3 new strawberries that you wanted to classify. The idea is of this particular paper is that because you have such a large meta training data set, imagine a million classes in meta training and 3 strawberries that you're interested in classifying as the new task. The logics of your original network are themselves good enough representations of the new data of the strawberries. You shouldn't really throw away the last layer of the classifier because you've spent so much work learning all these parameters. And this has nice motivation from some recent work on representation learning, which really shows that the clusters that typical deep networks learn, the networks that are good at classification, are not very blobby. So if you think of fitting a Gaussian mixture model, it doesn't look like a very clustered Gaussian mixture model. These clusters really look like a complete entangled mess, so they don't look at all separated. That is why you don't want to throw away all this interesting structure in the final output space. The next step is simply to fine tune with the few labeled data from the new task, not very surprising. And you could also perform a transductive fine tuning if you have some unlabeled test data in addition to the labeled data from the new task. All you lose is latency, but you gain performance. We do a bunch of other tricks that are quite common and popular in applied machine learning these days. So cosine annealing of step sizes works very well. Mix-up regularization essentially is a very drastic convex combination of the images during training that tends to work well. 16-bit training speeds up your training by about 2x. We use very heavy data augmentation, so on and so forth, but the details are not very important. The idea is that this is a very simple baseline to perform classification of new categories. Here is how it looks. So the crosses in this particular picture, there are 5 different colors, 5 different classes of the new task. The crosses are what are the labeled labeled samples. So these are the features that I've projected them into a 2-dimensional space using Tisney, and these are the features of the labeled data. The little circles are the features of the unlabeled test data. So the one that I'm going to be tested upon. And focus on the purple cluster here, for instance. The support datum, the label datum was somewhere here. The purple circles, the translucent purple circles began somewhere here before I began my fine tuning. And as I fine tune my representation, the purple circles move towards the label datum. The label datum doesn't move very much in the embedding space. And of course, you may make some mistakes. For instance, this red dot has gone to a green cluster. So you got that wrong. But the idea is that this fine tuning is essentially free. It's some mashup of semi-supervised learning that you do at the cost of latency to improve your performance, simply because your classes are new and you could have earned, you would have gotten a large variance if you had just done vanilla fine tuning. Here is how it works. So I don't want you to read the entire table. What I want you to focus upon is that there are lots and lots of algorithms for this problem. This is a very popular problem, naturally, as people try to personalize machine learning models or specialize them to different applications. And the different columns here are different data sets that people try to run their models upon. Typically, for instance, if you take this particular paper called TADAM, it would learn one model for 1 shot setting, another model for 5 shot setting, another model for 1 shot tiered ImageNet, another model for 5 shot tiered ImageNet. And there is really no end to this business. If I give you 10 shot data at test time, you would be forced to learn a different model. What happens if you focus on this particular line here, the second last line, this is fine tuning without any transduction. And already you are doing as well as all the previous algorithms, which are much more sophisticated meta-learning algorithms, without even trying, essentially. This is the first trick that you would have thought of running. Train a model on the training set, fine-tune it on the few labeled data, and let's see how well it works. If you do transductive fine-tuning, you are doing way better than these existing algorithms. So for instance, the best algorithm in this column is something like 62% accuracy. Here you're getting 68% accuracy without using too many tricks. It is fine tuning at the end of the day. The point that I want you to take away from this is that meta learning is a very difficult um, definition to instantiate into a good algorithm. All these algorithms are meta learning based, but if you kind of forego meta learning and think in a very, very simplistic way of it as simply fine tuning, you perform quite well. You can run much larger experiments because you are running such a simple algorithm. So this is the largest experiment on few-shot learning that has been attempted. It is the ImageNet dataset, but the larger version of it. It has about 22,000 classes, 14 million images, and which kind of separate out very nicely as follows. So the first 7,000 or so classes are the ones that have more than 1,000 images each. These are the frequent ones: cars, cats, planes, people. The green ones are the less frequent classes, and you can see that on a log scale, the number of samples per class dies down quite drastically. So it's a very natural data set to use to test your systems test your systems that are trained on the blue region and that could be evaluated on the green region of your data set. If you do transductive fine tuning, one shot 5-way accuracy, so 5 new classes, only one labeled datum per class, these accuracies are as high as 89%. And this is a little surprising. So what that really tells you is that go and collect as much data about the frequent classes as you can and simply do fine tuning when you want to work well on new classes. You're going to do really well. With a few more tricks, you could push this up to 95, and at that point of time, you can deploy it on the cloud and be happy. One shot 20 ways, so 20 new classes with only one labeled datum each, a very, very hard clustering problem. Even that accuracy is as high as 70%. You could push it to 80 with many more tricks. At the point that I would like to make is that these systems are good enough to be deployed at these accuracies. All you have to do is think about them in a slightly more simplistic way and regularize correctly. I think the reason most of the previous architecture did not realize this, and I don't want to dwell too much on this slide, is really because we have been looking at tables like these in all these papers, and it's impossible to understand which algorithm is good and which algorithm is bad after looking at a table like this. So this is very typical of a lot of new fields in the area of deep learning, where we've been so focused on numbers that we put in as many numbers as we can in a particular paper without systematic and rigorous ways of evaluating these algorithms. So we kind of propose a slightly different way of evaluating them, what one would call area under the curve of the accuracy of your model on the y-axis and the hardness of a particular task, how difficult a task is in terms of clustering. 20-way one shot is a difficult problem than 5-way one shot. 5-way 3-shot is an easier problem than 5-way 1-shot, and that is exactly what the x-axis measures. And now you can kind of look at your model across all these different regimes and say whether the area under this particular curve is large or not. This is one nice way of evaluating these models. So I won't kind of talk more about this figure. You can read the paper for it. But that brings me kind of to the second part of my talk. The previous part of the talk can really be summarized as transfer learning is a good way of building few-shot image classification systems. And one would like to know, how much can I stretch this business? What is it that helps me do good transfer learning? When can I not do good transfer learning? And that is what I would like to talk about in the next remaining time. Let's take an example from computer vision. So here are a few different problems from this paper called Taxonomy, which tried to solve a lot of different tasks, and they would like to come up with claims of the following form. So if I'm interested in point matching, so matching descriptors across images, whether this particular point in this image is the same as this particular other point in the same in a slightly different image, that is what one would call a registration. If I'm interested in this problem, this paper claims that I should train my model to regress normals, so estimate normals given monocular images. I should train my model to do edge detection, and then I can fine tune very well on matching points, or I can fine tune very well on shading. And essentially, this paper takes a huge battery of tasks. It tries to figure out which tasks are easily accessible from which other tasks. And now, for some new person who wants to do point matching, they know that they should start from these two areas and then fine tune these models quickly instead of training from scratch. So we want to develop good transfer learning systems. We don't know how. So we kind of do this very brute force approach where we say, collect a bunch of tasks. Let's see which one of the which tasks are close to which other tasks. And now you may use these general principles to fine tune your models. How you fine tune from one task to the other task is completely unknown. So if you started from 3D edges and reached point matching and you did not get a good error, what is it that you should be doing? Should you be overfitting on the 3D images task if your objective is to do point matching? Intuition would say no, but at this point of time, there is really no mathematics that tells you that you shouldn't be doing it. Here is one way we could think about formalizing the problem. So I will allude to what is called the information bottleneck principle. This is really a generalization of rate distortion theory from information theory that Naftali Tishby started working on in the late 90s. And it goes as follows. So let's say I have a Markov chain. I have data X that leads to a representation Z that I would like to use to regress or classify some targets 1. So Z is some statistic of X that I'm interested in learning. I would like this statistic to be good enough to predict Y accurately. So that is what a statistician would call a sufficient statistic of Z for the task of classification. I would also like Z to be small. I would like it to be small, let's say in the number of bits that I need to store in the coding theory sense. I could think about information theoretic ways of reducing the complexity of Z and so on and so forth. Why do I want it to be small? Well, the answer really lies in this paper, and we'll talk about it in a bit. But information bottleneck really says that if you want a representation of Z that is good enough for X, what you should be doing is minimizing the mutual information of Z with respect to the data X. So the first term is the mutual information of X and Z, and maximizing the mutual information of Z and Y. So the second term helps you predict Y well. The first term enables you to throw away as much information about X as you can. And the intuition behind it is very simple. If I'm in the business of classifying dogs, you can think of the grass behind a dog as some kind of a nuisance factor that hurts my classification of dogs. If I remember a lot of information about the data of these dogs, about the grass, every single time I see grass, I may make a mistake and call it a dog, even if there was a cow on top of the grass. So I would like to throw away as much information about the image, the information about the image from the image that is relevant to the grass, while remaining good enough for the classification of dogs. That gives you one natural way of thinking about dysfunctional. And Stefano Sovato has been working on this along this line for a couple of years. And what they really show is doing well on one task, namely you classifying the labels Y, requires you to throw away information about X. And this is kind of obvious. You don't want to overfit on your data X, so you throw away all the nuisance information about the data X. But I would like to make the following statement. So if your purpose is not to classify Y, but to classify some other task, then you've really hurt yourself by throwing away information about your data. The only way you can do well on a new task is if you retain a lot of redundant information. There is really no other way you can hope yourself to be better. You're really hedging your bets by keeping a lot of redundant information about your current data in the hope that it is useful for some other task. If you throw it away, there is no way you can be better at transfer learning. You can be good at transfer learning. So here is how one would formalize this intuition. Let us choose some canonical task which helps us measure how much information we are throwing away. So we are clearly throwing away information from X. I would simply like to measure what is it that I'm throwing away. You could use any which task to act as kind of a thermometer on the amount of information. But there is one special one, the reconstruction of data where Y itself is equal to X is a very special task. It is kind of a superset of all possible tasks. And if you're doing well on this particular task, it necessarily implies that you will be good on every single other task, because I could simply reconstruct the data and then use this reconstruction to learn a representation for classification. So reconstruction is a very special, and it's a little difficult to think about what it even means to reconstruct the data exactly in a lossless fashion while coming up with a smaller representation z than the size of data. But we can dig into it later in the breakout session. So here is one architecture that we will focus on. You have a data X that is encoded into Z. I will denote the encoder as E sub theta. Theta are the parameters. This is the stochastic encoder. I'm interested in classification. So I will go from Z to my labels Y using a classifier that is C theta, Y given Z. I will secretly use a task that is reconstruction to measure how good Z is, and that is what the decoder's job is. So decoder is another stochastic decoder, which gives you an output X, a conditional on Z. And these three are the kind of models that we are interested in analyzing for. So here is an autoencoder. Most of you will know what the Shannon entropy is. Shannon entropy is simply the expectation of negative logarithm of p of x. It measures how difficult your data is. If the entropy is large, your data is complicated. If your entropy is small, your data is simple. There is a related quantity that is called distortion, and that measures how good your decoder is. So it is the log likelihood of the decoder, logarithm of d of x given z, averaged over samples z drawn from the encoder. And this simply measures how good is the reconstruction of the decoder. If I uncompress my zip file, do I get the same data back or not? So zip has a distortion of 0. A related quantity is what is called the rate. The rate measures the excess bits that are used to encode the representation of x. So it is simply the Kehl divergence between the encoding distribution E of z given x and some prior distribution. You can think about it as the Lebesgue measure on z if you wish, which I will denote by mz. Rate is simply the complexity of encoding your latent factors or your representation z. If the rate is large, z maintains a lot of information about x. If the rate is small, it can go to 0 because it's a Kehl divergence. Z does not encode any information about x. In that case, E of z given x will exactly be equal to m of z. Okay. This is rate distortion theory, and what you can show is the entropy of the data is a lower bound on distortion plus rate. And once you write it like this is well known as what is called the evidence lower bound. People use it to minimize the sum of R and D given by this particular Lagrangian. You can think about this as a variational framework to learn representations, variational framework to learn stochastic neural networks, so on and so forth. The idea is that it is an upper bound on the entropy of data, so you can minimize it until you reach the entropy of data. What I want you to think about is that the Lagrange relaxation, which is R plus lambda times D, where lambda is the Lagrange multiplier, is really expressing the fact that there is some optimal value of the rate, which is a function of only a distortion, given the variation family of your model and the data set that you're working with, that best sandwiches this inequality. Okay, and here is how one would go about understanding this. So focus on the picture on the right. The x-axis is rate, it increases towards the right. The y-axis is distortion. If I have a model class of infinite capacity, I will denote this by these solid black lines. If I have a model class of infinite capacity, I can pump down the rate to very low numbers and still get very zero distortion, but I cannot pump it down arbitrarily to be arbitrarily small. I am forced by what the entropy of the data itself is. So this point here is exactly the entropy of the data x. And in this particular case, I will choose lambda to be really, really large. So my distortion is 0 and my rate is quite small. If I choose lambda to be 0, then I can get a 0 rate, and I can get distortion that is arbitrarily bad depending on my the quality of my decoder. So I get the y-axis back. One very interesting facet of this particular Lagrangian is that for lambda equal to 1, you get an entire equivalence class of models that spans like a line of slope 1 from the entropy here of the data on the y-axis, the entropy of the data on the x-axis here. And typically, when you train variation inference models, people use lambda equal to 1. It's extremely hard for you to control which part of the line your model lies upon, especially for high capacity models, which neural networks are. So you could be at this particular point where your rate is 0. So your encoding is absolutely garbage, even though your distortion is very small. And this is something that you will see very, very often in applied papers on variation inference, where they get fantastic reconstruction results because your decoder is memorizing all the data, even if the semantic meaning of your representations is garbage. You could be on this particular side where you get a you could be on this particular side where you get small distortion at 0 rate. If your model class is finite, then this entire curve you can prove kind of lifts up and goes to become the right hand, the red line, in which case your model will span different points on the red line depending on what lambda you pick. What you can do is introduce another quantity into the mix. In addition to the rate and distortion, you can think of the classification error. The classification error is simply the error of the log likelihood of your true labels y drawn from the data set, given your encoding z, averaged again over your encoding z given x. So it is the standard classification error in variation inference. And you can write down a modified Lagrangian, which is a function of two Lagrange multipliers now, lambda and gamma. You can also think of similar related quantities that are called, let's say, the entropy of the model class. Entropy of the entropy as defined here by this expression is simply the posterior on your parameters given all your data. If this entropy is very small, that means there are very few parameters, different models that fit the same data. If the entropy is large, that means that you have a very large family and you can pick up any model out of these to fit your data. Here is what we can prove. So we can prove that there is a constrained surface that joins together all these variational quantities, the rate, distortion, classification, and entropy. And this surface is a convex surface. So just like I had rate and distortion in the previous image, I now have rate, distortion, and classification. And this surface is a convex surface. And what really happens during training is that you start somewhere outside this surface and you fall down at specific points on the surface depending on what your lambda and what your gamma is. If you pick a different lambda and gamma, you fall down to a different surface. You can now write the KKT conditions for this surface, and they really look as follows. So dr equals negative lambda times dd, negative lambda times dc, so on and so forth. And what this really resembles is the first law of thermodynamics. So if you remember the first law of thermodynamics, the heat that I pump into a system either goes in as the internal energy, du, or it goes in as entropy. So there is a term that would be like TDS, where in this case it will be sigma times ds. So just like an energy is preserved in physical processes, and that is really what the first law of thermodynamics expresses, information is preserved in this model. Information is preserved in this model by virtue of the fact that you have an encoder classifier working in tandem with a decoder. The first law of thermodynamics is nothing more than a statement about the continuity of this particular surface. As soon as you have a constrained surface that joins these functionals, you get this particular expression. This surface, I would like to emphasize, is a function only of your parametric family and the data set that you're working with. It is not a function of your training mechanism. It exists even if you did not train your model at all. You can kind of dig deeper into this surface. You can solve for what the answer F looks like. So F looks like a free energy. It is the expectation over your data of the negative log partition function, Z. And that is really the reason why we call this an equilibrium surface. So what you can show is that if you are minimizing certain loss functionals while minimizing, let's say, R plus lambda times D plus gamma times C, You would minimize a Hamiltonian, which is roughly the logarithm of all the stuff inside in the brackets. Doing so using mini batch updates or using a stochastic gradient descent style setting minimizes a free energy of this form monotonically. And this we've seen before in earlier works as this free energy decreases monotonically along the trajectories of the Fokker-Planck equation, etc., etc. And that is why we like to call this surface an equilibrium surface. When you start training, you're really in some non-equilibrium regime where you haven't quite reached this particular value of the free energy. And as you finish training or as you reach convergence, the name of the game is really to fall down to this particular value of the free energy. What you may be interested in doing now is to find all possible parameters theta of your model that have this optimal free energy that corresponds to this variational family. And here is how one would go about understanding this. So we take inspiration from thermodynamics again, and we define what is called a quasi-static process on this surface. So a quasi-static process in thermodynamics would be a reversible expansion of an ideal gas, so it doesn't lose energy. In this particular case, we would like our stochastic processes to always travel on this surface without leaving the surface, so without losing information or without dissipating information. And this is an easy constraint to write. So if I define J to be exactly the stuff inside the minimization, the expectation of the log partition function, I would like to change my parameters theta in such a way that the gradient of J with respect to theta is 0 for all my changes. And this is a constraint that I can impose on any process in my model. In particular, I can create what is called an ISO classification process. So this is a process that comes with two conditions. First, the first one is a quasi-static condition in which is really trying to say that your parameters in the model are changing slowly so that they don't leave the surface. d by dt of the gradient of J equals 0. And then you can impose something that looks like dc by dt equal to 0. So I will change the parameters of my model in any which way that I can, but I'm forced to keep the classification loss constant. Roughly speaking, the information is being traded between the encoder and the decoder while keeping the classification loss constant. You can also do other things. For instance, you can impose C plus gamma inverse times R to be constant, in which case you would be learning a Bayesian neural network between C and R while automatically tuning D using this constraint. Here is how it looks. So in practice, you can kind of boil down these equations into the following set of equations. So lambda dot is equal to negative alpha times, I think there is a typo here. So it should be dou square F over dou gamma square. So these look really like second derivatives of the free energy F with respect to your Lagrange multipliers. And you can minimize these things using simple finite differences. So you can always evaluate these functionals like free energy by doing mini batch updates and taking averages over your latent Z's and update your parameters Lagrange multipliers lambda and gamma to go from, let's say, one value, lambda 1, gamma 1, to some other value, lambda 2, gamma 2, while always remaining on this surface. This is very powerful. So you start at some point on the surface. I can give a process which goes to any other point on the surface while respecting constraints, let's say, that keep the classification loss constant. And here is how it looks. So in this particular case, we took a small model on MNIST, and we designed an isoclassification surface, a process. Your model really begins at lambda equal to 0.25 and gamma equal to 4. It falls somewhere on the surface, and then we change lambda and gamma to some arbitrary values while keeping C constant. So the blue line has a constant validation loss, while rate and distortion are being traded automatically by the stochastic process in the during this time. You see the same thing for CIFAR. Let us not worry about it. The interesting thing that we do here in this business is going along the surface, as most physicists would know, is very slow. So the surface is an equilibrium surface. Equilibrium processes are much slower than non-equilibrium processes. So instead of going along the surface, we do these little hops. by increasing the temperature and then bringing it back down immediately onto the surface to wait for your next hop. And you can do this hops pretty easily by simply tuning the learning rate. And that is how it helps you get very far away from your initial lambda and gamma on the surface. But here comes the key idea. So once you have this surface is only a function of your parameters and your data. No one is stopping me from changing the data under the surface. I can take my data set, which is really given by distribution P of x comma y. I can move it from some source distribution PS to some target distribution PT. In this case, using a straight line, we also show results with some optimal transport style movement in the paper. And while this data set is changing, I can still explicitly create this constant. I can force the classification error to be constant across this entire movement. And this is very powerful. It is a completely controlled mechanism to transfer representations, and your classification loss is unchanged upon going to the target dataset. There is really no method that I know for satisfying these constraints across the transfer learning regime. You really try to tune on the target dataset, and you accept whatever error you get. There is no control that you get over this business. Here are a few experimental results. So we took one source dataset, MNIST digits 0 to 4, one target dataset, MNIST digits 5 to 9. And what I'm showing you here is one execution of the ISO classification process. The orange line is the model that was trained on 0 to 4. It started at this point of time. And the orange line is the result of the ISO classification process. And you can see that the classification error is roughly constant. If I do not do this business, if I just do what is done in standard transfer learning, I will get the blue line, which has a very low error on the target dataset before I start training, not surprisingly. As I train, the accuracy increases, a very low accuracy in the beginning. And as I train, the accuracy increases. And in this particular case, because MNIST is an easy dataset, I match the accuracy of the blue line and the orange line. The green cross is the accuracy of training directly on the digits 5 to 9, and all these three are the same in this particular model. If I take a slightly more difficult data set, if I want to go around all the vehicles in CIFAR 10, let's say 4 vehicles to 6 animals in CIFAR 10, I get a picture of the following form. So in this particular case, the orange line does not quite satisfy the classification constraint, but it is not terrible. So you are leaking some classification accuracy, but you are still way better than what you would have done by simply fine-tuning on the target dataset, which is the blue line. If you directly trained on the target dataset, you get something that is slightly worse than what you get by running the ISO classification process. So the point to take away from this experiment is not that the orange line is above the green line, but really that the orange line gives you control over where you are going to be. This is, of course, modulo some caveats in the sense, how far is the target data set from the source data set, how large is your model, etc., how accurately you estimate run the stochastic processes. But at least in some baby cases, we've been able to show that you can control the classification error as the data set changes under you. So to summarize, we talked about transductive fine-tuning. And we showed that it works extremely well, a little too well for the purpose of future classification. And the real reason is that neural networks are extremely powerful function approximators. We've been able to fit really anything we wish with these models. So instantiating frameworks of learning, in particular meta-learning, is extremely finicky and fragile in the world of neural networks. These frameworks just simply they have too many moving parts for you to be able to do a good job without overfitting them on data. The RDC surface, the equilibrium surface that we've been talking about, in my opinion, is a fundamental quantity that relates to representation learning, certainly very useful for transfer learning. And it also unlocks a lot of new ideas as to what regularization means. So typically we think of regularization as happening on the parameter space. Weight decay is on the parameters, the norm of the parameters. You can also think of regularization as happening in the function space. The rate, distortion, or the classification error are simply functionals of your model family. And by automatically trading them off against each other, you are coming up with different ways to regularize models that look extremely different from what we've been studying in machine learning until now. To end with sort of a punchline, I think until now, in the era of big data, we did extremely well. And we did extremely well in spite of not understanding very much of what data is. The name of the game was to collect as much data as you want about your problem and then simply fit a large network. This doesn't work well if you don't have a lot of data about your problem. So in order to do well in the new regime, which is really about as little data as you can or adapt as quickly as you can adapt, you really need to understand basic principles of what helps transfer and what hurts transfer. And this is the kind of work that we would like to do in the future. Understand what are the basic principles that govern transfer learning instead of simply creating good algorithmic ways of doing transfer learning. You can email all questions to this email address and read more about this work here. So I really talked about the first and the fourth paper. We have a few more papers that delve more about or towards fine-tuning, that talk about how you can incorporate these ideas into reinforcement learning to create good reinforcement learning algorithms. In reinforcement learning, there are a few other moving parts, but reinforcement learning also has a few things going for it because the data is not that complicated, and you can do clever tricks on top of your transfer learning to get more data from your past. This is where I would like to end, and I'll take questions if you have them now.